Almost every server that matters runs Linux. Your company SIM, your cloud, your containers, the web server you are defending right now. And here is what that means for you. Attackers don't target Linux by accident. They target it because that's where the value is. But most beginners learn Linux in the wrong way. They memorize a list of commands and forget them in a week. You are not going to do that because a SOC analyst doesn't need to be a Linux administrator. You need to understand how the system thinks, where it keeps its configuration, where it writes down what happened, who is allowed to do what, and where an attacker would hide. We start from absolute zero. By the end of these two videos, you will look at a Linux box the way an investigator looks at a crime scene. I am Netra. Stage 2 begins now. 5 parts in this video. Each one builds on the last. First, what Linux actually is. The thing nobody explains properly. Second, the architecture. 4 layers and the one attackers want most. Third, file system. Where everything lives and where evidence hides. Fourth, the shell and the two commands that do most of an analyst's work. Fifth, users and permissions. Who can do what and how that gets abused. No memorizing. Let's start with the first topic. What Linux actually is. In the part A, we will start with the definition nobody gives you. Let's start with the thing that confuses every beginner. Linux is not an operating system you install. Linux is a kernel, one single program that sits between your software and your hardware. It is written by Linus Torvalds in 1991, released free and open source, meaning anyone can read the code, change it, and ship their own version. So, what do you actually install? A distribution. A distribution, distro, is the Linux kernel, plus everything needed to make it usable. A shell, system tools, a package manager, sometimes a desktop. Ubuntu is a distro, Debian is a distro, Red Hat, CentOS, Fedora, Kali, Alpine, all distros. Same engine, underneath different packaging on top. Why does that matter to you? Because once you understand the engine, every distro you ever touch feels familiar. The commands change slightly, the concepts never do. Now, the design philosophy. It explains why Linux behaves the way it does and why it's a joy to investigate. Rule 1. Everything is a file. Your documents are files, obviously, but so is your hard drive, your keyboard, and your network connection. Even a running process is exposed as a file, which means one set of tools can inspect the entire system. That's enormous for an analyst. Rule 2. Small tools that do one thing well. Linux doesn't ship one giant program that does everything. It ships hundreds of tiny ones. One search text, one list files, one filter lines, and you chain them together to build exactly the tool you need on the spot. And rule 3. Text is the universal interface. Configuration is text, logs are text, command output is text. No hidden binary formats you can't inspect. Which means if you can read text, you can read the system. And rule 4. The one that defines security. Linux is multi-user from the ground up. It was built assuming multiple people share one machine. So every single thing on the system has an owner and set of rules about who is allowed to touch it. That assumption is the foundation of everything in the permissions sector later. So why the SOC cares? So why does a security analyst learn this at all? 3 reasons. 1. Your tools runs on it. Splunk, LStack, Zeek. Almost every security platform you will ever touch is deployed on Linux. 2. Your evidence lives on it. When a Linux service is compromised, the answers are on that machine. Logs, processes, configuration, timestamps. If you can't navigate it, you can't investigate it. 3. The threats are real and growing. Linux malware is no longer rare or crude. Modern Linux threats include full remote access toolkits, credential harvesters, and the rootkits that hide themselves at the kernel level. Cloud, containers, and critical infrastructure all run here, which means attackers invested here. So, not administration, investigation. That's the lens for everything that follows. Linux architecture. Linux is built in layers, 4 of them. Get the stack, and everything else clicks into place. At the very bottom, hardware, CPU, memory, disk, network card, the physical machine. Above it, the kernel. This is Linux itself. The kernel has 4 jobs, and they are worth knowing by name. It manages processes, deciding what runs and when. It manages memory, deciding who gets what and keeping programs apart. It manages devices, translating for 4 hardware through drivers. And it manages the file system, reading and writing your data. Nothing reaches the hardware without going through the kernel. Nothing. Above the kernel, the shell. Your interface to the system. You type a command, the shell interprets it and asks the kernel to do the work. And on top, applications. Everything a user actually runs. Hardware, kernel, shell, applications. 4 layers, that's the machine. Part B. Kernel space versus user space plus system calls. Now, the distinction that matters most for security. The system is divided into 2 worlds, kernel space and user space. Kernel space is privileged, total control of the machine, direct access to hardware and memory, no restrictions. User space is restricted. Every normal program lives here, your browser, your web server, your text editor, and write this down, your security tools live here too. So, how does a restricted program is user space ever get anything done? It asks through sometimes called a system call. A system call is a formal request from user space into kernel space. Open this file, send this data, start this process. The program can't do those things itself. It asks the kernel and the kernel decides. This is elegant security design. The dangerous power is isolated behind one control doorway, and every request through the doorway can be checked, but it has consequences. Every answer your program receives comes from the kernel. Hold that thought, it becomes the entire code open of part 2. Part C. Kernel modules and the advanced piece. One more thing, and this is where every beginner becomes dangerous. The kernel isn't frozen block of code. It can extend it while it's running. Those extensions are called kernel modules, loadable kernel modules. Usually, they are completely legitimate. A driver for your graphic card, support for a file system, networking features. But think about what a kernel module actually is. It's code running inside kernel space with full privilege below every security tool on the machine, which is exactly why the most serious Linux malware is built as a kernel module. Because a rootkit loaded there doesn't have to hide from your tools. It can change what your tools are told. There is a newer version of this problem too, eBPF. It's a modern technology that lets code run safely inside the kernel, and it's genuinely brilliant for performance and monitoring. Defenders use it, and now so the attackers. So here is a mental model to carry forward. The higher up the stack you are, the more you can be lied to. And the deeper an attacker gets, the harder they are to see. That's why the kernel is a price. And the now file system hierarchy. In Windows, you have drive letters C drive, D drive, and E drive. Linux has none of that. Everything hangs off a single root, one forward slash. Every disk, every USB stick, every network share gets attached somewhere inside that one tree. That's called mounting. So, there is one path to everything, one structure to learn. And the structure isn't random. It follows a standard, which means the directories you learn on Ubuntu are in the same place on Red Hat. Let's walk that ones that matters to an analyst. Part B, the directories that matter, slash etc. Configuration, the brain of the system. Every services settings lives here. The list of user accounts, scheduled tasks, network configuration lives here. When an attacker wants to change how this machine behaves, they become to slash etc., which makes unexpected changes here very loud. Slash var, variable data, things that grow and change while the system runs, and inside it, the single most important directory in the entire video. Slash var slash log. This is where the system writes down what happened, logins, errors, service activity, authentication. Your investigation starts here almost every time. We'll spend serious time on it in part 2. Slash home. Each user gets their own home directory here, their files, their settings, etc. Slash root. And note this carefully. That's the super user's personal home directory. It is not the same thing as the root of the file system. Two different things, same word. Beginners mix them up constantly. Slash TMP. Temporary files. And here is the security relevant part. It's returnable by everyone on their system, which makes it a favorite landing zone for malware. And attackers with limited access can almost always write to slash TMP. So, a program executing from a temporary directory is one of the loudest signals in Linux. Legitimate software doesn't live there. Slash bin and slash sbin. The actual programs that commands you run and the system binaries reserved for administration. A classic attacker technique is replacing one of these trusted binaries with a poison copy. You run a normal command and gets the attacker's version slash user slash op slash boot slash user additional software and libraries slash opt optional third-party packages slash boot the files needed to start the machine including the kernel itself and slash dev where your hardware appears as files. Remember rule 1, everything is a file. This is where that becomes literal. Part C, slash process and hidden files, the advanced piece. Now, the directory that makes Linux special for investigators, slash process. Here is what make it different. Slash process doesn't exist on your disk. It's generated live in memory by the kernel. It's a window into running system presented as files. Every running process gets its own directory in here named by its process ID. Open it and you can see what command started it, what files it has opened, what memory it's using, what network connection it holds. There are also system-wide entries, CPU details, memory statics, loaded kernel modules, active network connections. For an investigator, slash process is as close as you get to reading the system's mind in real time. And it has one more property that matters enormously because it's generated by the kernel. It's often where analysts go to cross check what other tools report. If a tool says one thing and slash pros says another, that discrepancy is a finding. Last piece, hidden files. In Linux, any file whose name begins with a dot is hidden by default. A normal directory listening won't show it. You have to explicitly ask. That's not a security feature, it's a convenience for config files. But it's also a gift to attackers. A malicious file named with a leading dot sitting in a user's home directory is invisible to anyone who doesn't know to look. So, the habit to build where you investigate a directory always asks to see everything. Shell and command line. What the shell actually is. The shell is the program that takes what you type and turns it into action. You type a command, the shell interprets it. It asks the kernel to do work. The result comes back in your screen. The most common shell is bash. They differ in features, not in concept. And why do analysts live in the terminal instead of a graphical interface? Three reasons, and they are all practical. Speed. A command executes instantly on a server with no desktop installed, which is most servers. Precision. You get exactly what you asked for, and you can prove exactly what you ran. And composability, the big one. You can change small tools into a custom tool on the spot. No graphical interface lets you do that. There is also something worth knowing about how the shell finds commands. When you type a command name, the shell searches a list of directories to find the program. That list is called the path. Why does an analyst care? Because if an attacker can modify a user's path, they can make a malicious program run instead of a legitimate command. You type something normal, you get something else. Part B, the commands that matter. You don't need hundreds of commands. You need a small set understood deeply. Navigation. ls lists what's in a directory. cd moves you between directories. pwd tells you where you currently are. Reading files. cat prints an entire file to your screen. Fine for small files. Less lets you page through a large file, scroll and search inside it. And log files are large, so less is the one you will actually use. Head and tail show you the beginning or end of a file, and tail can follow a log live as new lines arrives. Now, the two that carry an investigation. grep. grep searches for a pattern inside files. One file login buried in 200,000 log lines. grep find it instantly. One suspicious IP address across a dozen different log files. Same command. If you learn one Linux command as a security analyst, it is this one. Find. Where grep searches inside files, find searches for the files themselves. By name, by size, by owner, by permission, and critically, by time. Every file modified in the last 24 hours, every file created since the incident began. That's how you scope an intrusion. How you figure out what an attacker actually touched. Together, grep and find answer most of the questions you will ask a Linux machine. Part C, streams and pipes, the advanced piece. Now the concept that turns commands into a toolkit. Every program on Linux has three standard streams. Standard input, where it reads from. Standard output, where its normal results go. And standard error, where its error messages go. Keeping output and errors separate sounds like a small detail. It isn't. It means you can capture results without the noise or capture only the failures. You can redirect these streams, send output into files instead of the screen, append it to an existing file, and then the pipe. That vertical bar takes the output of one command and feeds it directly into the next as input. Such a huge log for one IP. Pipe that into a filter that counts unique entries. Pipe that into something that sorts by frequency. Three simple tools, one line, and we have just built a custom analysis tool that didn't exist a second ago. That is the entry Unix philosophy in action. And it's the reason a skilled analyst in a terminal can outrun someone clicking through a graphical interface. Two last things to know exist. Environment variables, settings the shell keeps in memory that programs read. Path is one of them. Attackers manipulate these. And Tmux, it splits one terminal into multiple panes and keeps your session alive even if you disconnect on a long remote investigation. Users, groups, and permissions. Linux was built multi-user from day one. So every security question here reduces to two things. Who are you and what you are allowed to do. Every user has a numeric ID, a UID, and one UID matters more than all the others. UID 0, root, absolute power, no restrictions, root can read anything, change anything, delete anything, and disable anything watching it, which is why the golden rule exists. You do not log in as root. Instead, you use sudo, temporary elevated permission for one command, and critically it gets logged. That logging is the point. Sudo creates an audit trail. Who became powerful, when, and to do what. The files that holds identity, slash etc, slash passwd. Despite the name, it holds no passwords anymore. It lists every account, username, user ID, group, home directory, and the shell that account gets when it logs in. Watch that last field. Service accounts, account that exists for software, not people, should normally have no login shell. If a service account suddenly has one, someone gave a machine the ability to do login. That's a finding. Slash etc slash shadow. This is where the actual password hashes live. Readable only by root. If any ordinary user can read shadow, you have a critical problem immediately. And slash etc slash group defines the groups. Groups exist so permissions scale. You grant access to a group, not to 20 individuals. And one group deserves constant attention. And the pseudo group called wheel on some systems. Anyone in it can become root. An unexpected new member of that group is one of the loudest signals in all of Linux security. Part B, the permission model. Now, permissions. This intimidates beginners. It shouldn't. It's tiny. Every file answers three questions for three audience. The audience, the owner, the group, and everyone else. The question, can you read it, write to it, execute it? Three permissions, three audience, 9 slots. That's the entire model. One subtly worth knowing because it catches people out. On a directory, those permissions mean slightly different things. Read lets you list what's inside. Write lets you create or delete files in it. And execute lets you enter it at all. You will also see permissions written as numbers. Read is 4, write is 2, execute is 1. Add them up. 7 is read plus write plus execute. Full control. 6 is read and write. 5 is read and execute. So 755 means the owner can do everything and everyone else can read and run it. Very common and sensible. And 777 means every single user on that system can do anything to that file. 777 is almost always either a mistake or a deliberate backdoor. Mod changes permissions, on changes ownership, unexpected use of either on a system file is worth investigating. Part C, special bits and ACLs, the advanced piece. Beyond the 9 slots, there are 3 special bits and one of them is a genuine attack path. SUID. Set user's ID. Normally, when you run a program, it runs with your permissions. SUID program runs with the permissions of its owner instead. So if a program is owned by root and has SUID set, then any user who runs it briefly acts as root. There are legitimate reasons for this. The password changing tool needs it. An ordinary user has to write into a file only root can touch. But now think like an attacker. If you have got limited access on a machine, you want root. So you hunt for SUID programs, especially unusual ones, or one that let you run other commands. Find a misconfigured SUID binary and you write it straight to root. This is one of the most common privilege escalations path in Linux. There is sgid, which does the same thing for groups, and the sticky bit, which is actually a protection. On a shared directory like /temp, it means users can create files, but can only delete their own. Without it, anyone could delete anyone's files. Finally, ACLs, access control lists. Standard permissions only understand one owner and one group, but real environments are messier than that. Sometimes you need to grant one specific extra user access to one specific file. ACLs lets you do that. Fine grained by user permissions layered on top. Powerful and easy to misconfigure, which is why they are worth checking. A file can look correctly locked down in a standard listening, while an ACL quietly grant access to someone else entirely. That's your foundation and it's a real one. You know what Linux actually is: a kernel, wrapped distributions, built on 4 design rules that shape everything. You know the architecture, hardware, kernel, shell, applications, and that user space as kernel space for permissions through system calls. You know the file system, etc. for configuration, var log for evidence, temporary for malware, proc for live truth, and that a leading dot means hidden. You know the shell, grep to search inside files, find to scope by time, and pipes to build tools on the spot. And you know identity and permissions, root, sudo, the 9 slots, and SUID as a privilege escalation path. Everything so far has been how the system works. In part 2, we use it, processes, and how to spot a malicious one, services, and how malware uses surveys a reboot, packages, and how attackers gets you to install them yourself, and logs, where every investigation actually begins. The part 2 is where this becomes a security skill. Subscribe to Trinetra SOC right now. Hit the notification bell so you never miss a single video. The digital world needs defenders. I am Agent Netra and I will see you in the next video.